Hello, my name is sgrizzar. This is Calculus 1, Lecture 2B, using two cops and a drunk and writing proofs. So today what we want to emphasize, last time we talked about limits and we stated what two cops and a drunk was. Today what we want to do is we want to talk about how to write up proofs. And we want to kind of undo some high school geometry damage. No, proofs, no, geometry. We don't want to have flashbacks on geometry. So what we want to do is first of all state what a proof is. A proof is just a mathematical argument. It's just an argument. It's sort of like writing a 5-paragraph essay in English, okay? You've got an introduction, you've got some body, and then you've got a conclusion. Now, the big difference is that what we want to do is have a logical sequence of arguments that convinces a mathematician. But again, it's still an argument, and it has a little style, and it's not like, where this, then this, then this, then this, then this kind of thing was where you had the big grid that you had in geometry. We don't want to do that. We want to do a narrative proof, something a little bit more friendly. So let's talk about how to do this. The way that you write it is kind of like you write an English paper. You have an introduction, you have a body, and you have a conclusion. Okay? And we'll do some examples. So the first example that we're going to do is we're going to do the one that we did in problem set 2, which was the direct substitution property on a polynomial. Then we'll talk about some two cops proofs. We'll do one of the classics, x sine 1 over x, the limit is 0. And then we'll do some of these picture proofs, which the picture proofs don't really show up on tests. Two cops shows up on tests, and proofs with two cops shows up on tests. But they illustrate the power of this method, where you get the thing you want trapped between two things, and then you take it to the limit that you want it to go to. So for in that vein, we're going to do the limit as x goes to 0 of cosine of x equals 1, and we're going to prove this special limit. In the notes, additional things, the notes, which you can find the link to down there in the description, there are additional proofs and examples of additional proofs in the notes. Along with things like the limit as x goes to 0 of sine of x equals 0. And believe it or not, those are important things to prove. They look obvious when you look at the graph, but you kind of have to prove them. And by doing this, you build up a system of proofs that we're eventually going to be able to, in problem set 3, prove that sine has the direct substitution property, cosine has the direct substitution property, and you'll be able to prove that the derivative of sine is cosine. So that's kind of the point of problem set 3. All right, so we're going to start with the limit laws that we did in problem set 2. We had, and we're going to prove, so among the other proofs, among the other limit laws, we had the sum law, the constant multiple law, the natural power law. These were kind of the intermediate steps. And then we had these two finishers, the limit of the identity and the limit of the constant. So to show you how they work together, here, what I'm going to do is show that I'm going to use the limit laws to compute the limit as x goes to 2 of 3x squared plus x. The first thing I do is I break it up using the sum law here. Then I use the constant multiple law to pull the 3 off there. And remember that we had this idea of PEMDAS. So we had the idea, please excuse my dear Aunt Sally. My dear Aunt Sally, right? So this is what we did. We did parentheses, exponents, multiplication, division together, and then addition and subtraction. And when we execute, when we do orders, so execute is this way. So this is, we pop things. When we pop things or when we break up stuff, we go this way. So when we evaluate limits and things like that, we're actually going to evaluate them outside in. So the last thing to happen is the addition, right? X gets squared, then it gets multiplied by 3. Here it goes in as x. And the last thing to happen is that these things get added together. So please excuse my dear Aunt Sally is together, right? Addition to subtraction is the last thing. So the first thing we do when we kind of peel apart the onion is the last layer. So the last layer of this onion is the sum. What we're going to do is we're going to peel that off with the sum law and get 2 of these here. Now, the constant multiple, the multiplication happens, the step before addition, the multiplication happens. So I need to pull that off next. Okay, so I peel that layer back, then I pull back the layer that's done with the exponent. So I use the natural power law to do that. And then what I do is I then have these two things, the limit as x goes to 2 of x, and the limit as x goes to 2 of x. Now this matches my rule about the limit of identity. So I take a, in this case 2, and I just sub it in directly. I sub it in using the limit of the identity, and I have 3 plus 2 squared plus 2. I add those things together, right? So I got 4, 12, 13, and 14, and I add them all together, and I've evaluated. So that's how we evaluate these limits. Now, the direct substitution property is we let f be a function. F has the direct substitution property if for every a in the domain of f. Now, this is weird. A is now something that we pick our a, fix it, and then we say the limit as x goes to a of f of x equals f of a. And it's the I can just plug into x property. That's the way to remember it. So, for example, for all a, the limit as x goes to a of x plus 4 is a plus 4. The limit as x goes to 2 of 3x squared plus x, we directly substitute in there. If we get 3x squared, we get 3 times 2 squared plus 2 equals 14. And I mentioned this last time, and I gave you an example last time of one who can't. So this is cannot do ds. So you can't do direct substitution on a function that looks something like this, right? So if I had here, let's say I've got this function here, which is absolute value, right? So f, we'll say that this is 2, and we'll let that be 4. So f of x equals negative x if x is less than 0, x if x is greater than or equal to 0, and x does not equal 2, and then 4 if x equals 2. Okay, so I have this weird function here that's the absolute value, except at 2, which the value is 4. And so if I want the limit as x goes to 2 of f of x here, I want to talk about what happens around 2. Not what happens at 2, but what's going on around 2. And around 2, the answer is 2. Around 2, this function is 2. Okay, not at 2, but around 2, right? So this is not equal to 4, so I cannot do direct substitution on a function that has this. It's got a little jump in it. Okay, so what we wanted to prove, remember, was to prove that polynomials have this direct substitution property. Remember that P is a polynomial if for all x in the x space, P of x equals Cn x to the n, Cn minus 1, blah, 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 down to C0, where the n is, of course, where n is a positive integer and where all of these things are constants. Okay, and I think I used a in one set of notes, and I'm using Cn's here. They're just constants. Okay, so, and then here is my theorem. Okay, so now what I'm going to do is I'm going to say if f is a polynomial, then the limit as x goes to a of f of x equals f of a. Now, the key here is to figure out what you really need to show. What I need to show is that I can stick a in for x and just get f of a. So f is a polynomial. So what I really want to show is that the limit as x goes to a of the polynomial, cn x to the n plus cn minus 1 x to the n minus 1 plus blah, 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 plus c2 x squared plus c1 x plus c naught equals cn a to the n plus blah, 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 plus c1a plus c naught. And then I'm going to have a strategy here. I'm going to apply limit laws in order to get this to happen. And notice once you say what you're trying to do, you've actually almost finished the proof. Now it's just applying limit laws. And even if I didn't give you this, even if I didn't show you the stuff in blue, based on these instructions, you should be able to generate the proof fairly quickly on your own without having to look at anything else. So I take the thing on top, right? This is my p of x. And then I apply the sum law and I break it up. Then I use the constant multiple law to pull off all the constants. Then I use the power law to pull off all the exponents. Then I apply the limit of the identity and the limit of a constant. So I'm actually doing two things here. Right? So I'm going to apply the limit of the constant to get rid of that one, and the rest of them are all limit of identity, and I get what I wanted. And then I say I did what I did, right? So for any polynomial f, the limit as x goes to a of f of x equals f of a. Okay? So notice here what I've done. I've said what I'm going to do. Then I said how I was going to do it. Then I did it, and then I said what I did. So the introduction, very short. It just says, what is it I want to do? What is it I want to show? I rewrite the problem in my own words. And then I apply, and then I say what strategy I'm going to use, apply the limit laws. And then when I'm done with this, chain of equal signs, as this one is, I'm just going to say what I did. So that's basically the structure of the proof. So next we want an example of using two cops. So let's prove this little fact. And this is similar to an exercise in the book. The limit as x goes, let's show that the limit as x goes to a of x times sine 1 over x equals 0. Now, recall that the limit as x goes to 0 of sine 1 over x does not exist. This thing never settles as you head to 0. It just goes brrr, oscillating very quickly. So I can't use the product law. I cannot break this up using the product law. But if you graph this function, you'll see something very interesting. There's a function here above this and a function below that trap this function. So this function x sine 1 over x is actually going to have a limit. And so what we need to do is we need to find the two things. Then we need to use two cops. So recall what two cop says. So remember what this says. This says that if for all x near a, bot of x is less than or equal to f of x is less than or equal to top of x, and the limit of top of x equals the limit of bot of x equals L, then the limit as x goes to a of f of x equals L. So if I want to use two cops in a proof, I need to show the two conditions are met. And I'm going to do that in a narrative form. I'm not just going to have symbols. I'm going to have actual words here. Now, if we look at the graph, we already get a hint at what's going to happen. This thing on top is probably going to be the absolute value of x. I don't know that for sure yet. I haven't shown that. I haven't proved it. But if we look at the graph, we get the intuition that this is probably going to be absolute value of x. Likewise, the bottom function is probably going to be negative absolute value of x. And this, of course, gets into what the absolute value actually equals, which is actually, the absolute value is a piecewise function. And we'll show that when we do this proof. So let's look at what I'm going to do here. This is kind of my intuition. This isn't my proof, but this is my intuition. The first thing I'm going to do is say what I want to do again when I want to write the proof. So let's do a little want to show. What is it I want to show? I want to show, and again, I want to rewrite this a little bit. Here, I've written this in terms of kind of a limit as x goes to a. So I'm just going to rewrite it. I'm just going to say that as x goes to a, sine x times sine of 1 over x equals, I'm sorry, this goes to, not equals, goes to 0. All right, so I'm just going to rewrite it a little bit, saying as x goes to a, this function here goes to 0. And my strategy is going to be to use two cops. And then since I have this picture here, I'm going to add a little intuition. Top of x is going to equal the absolute value of x, and bot of x is going to equal negative absolute value of x. So if I want to do this, I need to show two things. I need to show that my first condition is met here. I need to show that for all x near a, bot of x is less than or equal to f of x is less than or equal to top of x. And I need to show that everything is going to the same place, L. Okay? In this case, I need to show that everything goes to 0. All right, so here's how I'm going to do that. All right, I need to show that I meet the two conditions. Well, remember that sign is bounded between -1 and 1. Here, we can actually see it here. Here, I've got 1 up here and -1 down here. Sign is a bounded function. Okay, so I could say that. Okay, so for all x near a, so what I'll say is the range of sign is -1, 1. This is to say that sign is always trapped there. So sign of anything has to be between -1 and 1. So for all x near a, I know that -1 is less than or equal to sign of x, which is less than or equal to 1. Now, I'm sorry, sign of 1 over x. Okay, so that I know is true for all x's near a. For any x near 0, I should actually say instead of near a, I should say near 0. So for all x near 0, this is true. So now what I want to do is I want to multiply through by x. Now remember, if x is negative, I flip the inequalities when multiplying through. So I have to do kind of two different cases, right? I've got to say, okay, if x is less than 0, likewise, if x is greater than 0, I don't flip them. So I now have shown that the thing I want in the middle is my f. This is the thing I want. So now I'm going to construct my bot and my top. So now I have a bot and a top that work, right? If x is less than 0, negative x is on top. If x is greater than 0, then x is on top. And likewise, bot would be x if x is less than 0, and negative x if x is greater than or equal to 0. Now, it turns out that this right here equals the absolute value of x. This right here is the definition of the absolute value. If I've got a negative number, I want to make it a positive number. I do so by multiplying it by -1. Okay, because a negative times a negative is a positive. So that's actually the definition of absolute value of x. It is a piecewise function. Okay. All right, so now I've got this piece here. This means that I've satisfied condition number 1, right? Condition number 1 was that for all x near a, bot of x was less than or equal to f of x is less than or equal to top of x. So now I can say condition 1 is satisfied. Now what I need to do is satisfy condition 2. So now what I need to do is take the limits of these, okay? So the limit, I've got a limit here as I go to 0 from the left. That means I'm less than 0. So I'm going to use this part of the definition of bot. Okay, so I used the various definitions depending on where I was to see now that the limit of these things is equal, the limit of these things is equal, right? So the limit from the left equals the limit from the right, the limit from the left equals the limit from the right, and I know. Okay. Now I've met both conditions of 2 cops and a drunk. This right here met my first condition, and this right here met my second condition. Now, notice here what I'm not doing is I'm not writing limit signs on the sign on either side of an equation or an inequality. I can't really do that. The limit is really not a function, okay? So I can't just take the limit of both sides of an equation, okay? Because I wind up in things that aren't actually true, especially if the limit doesn't exist, and it doesn't respect inequalities that are strict. It only respects non-strict inequalities. So it's important to note that what I'm not doing is treating the limit like a function. So what I've done is I've shown both conditions. Now, what I'm going to do is I'm going to turn the crank, okay? Two cops and a drunk says that if these two things are true, then this thing must be true. This is math. It's not some humanity. It's not some social science thing where we say, oh, well, this is sociology. We say that in general, this is true. And if this is true, then in general, most of the time, except on weird Tuesdays, this is true. No, no, no. This is math. If this is true and this is true, then this must logically follow. That's what a theorem means. This must logically follow. This must be true. Okay? So it must be the case by two cops, the limit as x goes to 0 of x sine of 1 over x equals 0. That must be true. And then I'm going to write Q, E, D at the end. And this is sort of my tagline. I've done what I wanted to do. I've shown it. I've stated my theorem. And I say, thus, by two cops, the limit as x goes to 0 as x sine 1 over x equals 0. And then I say QED, which is Latin for neener, neener. Okay. So what did I do? I said what I was going to do. I did it. And then I said how I was going to do it. Then I did it. And then I said what I did. So notice here what I did. I had two conditions that I had to show I meet in order to use this theorem. The first was to show that I had a top and a bot so that for every x near A, or every x near 0 in this case, top was bigger, bot was smaller. In a non-strict sense, right? Less than or equal to was the thing we wanted. The other thing I needed to show was that everything went to L. So L here was 0 as well. So as the x went to 0, top went to 0, and bot went to 0. And for this one, I actually had to break it up. So for the example that's in your book with x squared, that's always positive. So you don't have to do this break it up. You can treat both sides at the same time. But here, because x, can be negative or positive, I kind of had to break it up and kind of treat each one individually. So that's how you use two cops. This next one we're going to do is one of these trig ones that you use two cops from. And the key to the trig proof ones is that you need a diagram. Okay, so let's look at this diagram. We want to show that the limit as x goes to 0 of cosine of x equals 1. So let's write a little introduction. What we're going to say is, what do we want to show? We want to show that as, let's see, cosine of x goes to 1 as x goes to 0. Okay, and how we're going to do it, our strategy is going to be strategy. Use the diagram, noting that this triangle here formed by the sine and the cosine, 1 minus the cosine and the chord. Let's label that. That's a right triangle. So we'll label these sides A, B, and C. Okay. C is the chord, A is the sine of x, B is the 1 minus cosine of x. So what we want to say is that this here forms a right triangle. And what's important there is not that we have a right triangle, it's not that we have a area or that we have the Pythagorean theorem. What's important here is that because of the Pythagorean theorem, b squared, okay, b here must be less than c, because b squared, it's a squared plus b squared equals c squared. And so that means that b squared must be less than c squared, or because we're dealing in the positive case, b must be less than c. Noting that AB, the triangle formed by this ABC bit, is a right triangle. So a squared plus b squared is a right triangle. So b squared is less than or equal to c squared. Right? That's going to give us that b is less than c. And x here is the chord. I'm sorry, c here is the chord for x. So since c is the chord for x, c has to be less than or equal to x, right? If I'm moving along the circle, remember that the length of the chord is less than or equal to the length of the arc. And it's always less than equal to the arc unless the length of the arc is 0. Right? So it's faster to move along the chord of a circle than a chord of an arc than it is to move along the outside of the arc. And that's going to give us our 2 cops. So let's see what it looks like here. Okay, so here's the proof. Okay, so note from the diagram. And then the rest of the strategy. I have a major name theorem, so I want to name that my strategy. Okay, so what I'm going to do here is I'm going to use 2 cops on this diagram. Once I set up the inequality. So what do I have here? I don't care about A. I've got B and C. So what I'm going to say here is the following. I didn't spell that right. C. Now, remember what we're doing. We're letting x go to 0. Okay? So let's let x be right near 0. Right? So if x is right near 0, that means that everything here is positive. And b is less than or equal to c. Okay? And then, since c is the chord and x is the arc, we know that c is less than or equal to x. Now, since everything's positive, 0 is less than everything else. Okay, now I'm going to put together all this information. So thus, I know that 0 is less than or equal to the length of b, which is less than or equal to the length of c, which is less than or equal to the length of x. Okay, now, I don't need c. I'm going to ditch c because what I really wanted was that b was less than or equal to x. So this 1 minus cosine of x, I got that because this is the cosine and this whole length is 1. So this length right here must have been 1 minus cosine of x. That's a little tricky. We don't expect you to come up with that one on your own. All right, so now what I've got is I've got the 0 is less than or equal to 1 minus cosine of x is less than or equal to x. All right, now remember what I want in the middle is cosine. Okay, so, and I know that the limit, looking at the graph, I'm pretty sure that the limit's going to go to 1. So how can I find, now this will already do it for me. I'm sorry, this right here will take me to 0, and this will take me to 0. And I've got this 1 minus cosine bit. So I want to get rid of this right here. So what I'm going to do is I'm going to subtract 1 from everything in the equality. Now remember, I don't flip the signs because I'm subtracting. Okay, I flip the signs when I multiply. So I'm subtracting. So what I'm going to get is negative 1 is less than or equal to negative cosine of x, which is less than or equal to x minus 1. That's good. Okay. So now that I've got this, notice here that all I'm doing, if I multiply through by negative 1, I would kind of have what I want. Because x is going to go to 0 here, and that's going to give me 0. This is going to be 1 minus x if I multiply through by negative 1. And remember, I have to flip the signs. So now I'm going to get 1 is greater than or equal to negative 1 cosine of x, which is greater than or equal to, I'm multiplying through by negative 1. That's going to become negative x plus 1, which is the same thing as 1 minus x. Okay. So I multiplied through by negative 1, and I got this inequality. Now I've got the thing I want in the middle. I've got something that will go to 1 on the left, on as for top, and I've got something that will go to 1 as x goes to 0. That's my bottom. So let bot. Now, remember, I'm talking about the right side here, not the left side. So I'm only talking about the positive side for the moment. Now, getting the left side, that you can do as an exercise. It's actually pretty easy. There are two ways to do it. The first is just to multiply through by a -1, flipping all the signs, and you'll wind up at the same place you were before. The other way to do it is to draw the diagram in the negative side. And then this right here will still be positive, 1 minus cosine. Cosine will still be positive, but the c and the x will all be negative. And then you just have, instead of having 0 on the bottom on this thing, you have 0 on the top. So you can do it either way. Okay, so what we're going to do is say, okay, the limit as x goes to 0 from the right of bot of x equals the limit as x goes to 0 from the right of 1 minus x. This right here is a polynomial. We can just sub in on it, and it equals 1 minus 0, which equals 1. And the other side is just the limit of a constant. So now, look at what I did. I set up my thing using a diagram, okay? Then what I got is I showed that I met the first condition by manipulating the diagram. Then what I did is I needed to show that the limit from both was the same. Now, it should be noted that I'm doing this here only for the bot. I'm going to leave as an exercise for you that it works on the other direction. I'm only proving that it works for the positive side of x. You have to show that it works for the negative side of x. Okay, so I showed here that the limit as x goes to 0, right, cosine of x equals 1. I'm leaving for an exercise, you to show. So that's just left as an exercise of the reader. Okay, so what we've shown actually is that this works if I'm coming from the right. Showing it works from the left is something you can do on your own. But look at the structure of this proof, right? I did the same thing I did before. I said what I was going to do. I said that my strategy was to use this diagram with b squared here is less than or equal to c squared. And notice that that is true even if I'm in the negative quadrant. Okay, so the c squared is still less than or equal to, I'm sorry, the b squared is still less than or equal to the c squared. But because these are negative, that's going to mean that c is going to be less than or equal to b, not greater than. But it still works. And then the chord argument will be that x is less than or equal to c because you're dealing with the negative side. Okay, the b is still positive, it still stays. Okay, but you'll see it works out. You can play with it. Matter of fact, since b is positive, c and c is negative, you already have that. And x is negative. Okay, so you can show the left side on your own. But notice that it's the whole thing is just a two cops proof with this little diagram in it. Okay, so let's look at one more of these big ones. This is one of the big trig ones. This is special limit 1. And this limit is going to be very important for us this week as we do problem set 3. And it is that the limit as x goes to 0 of sine x over x equals 1. In order to do that, the first thing we're going to need is we need two bits. The first bit we need is the bit we just proved, that the limit as x goes to 0 of cosine of x equals 1. And the second bit that we're going to need is this idea of the area of a sector of a circle. So a whole circle is 2 pi r around. So the portion of the circle that's covered by an arc x is x over 2 pi r, right? It's the whole thing was 2 pi r, and the portion that we covered is x divided by that. Okay? The area of the entire circle is pi r squared. Therefore, the area of the sector is the portion covered, x over 2 pi r, times pi r squared. The r, one of the r's will cancel, and the pi's will cancel. You'll get x over 2 times r. If r is 1, then the area of the circle of the sector is x over 2. So let's look here at what we have. So we're going to have 3 diagrams. Remember that this line that passes through here is the tangent line. The line that goes from here on up to here, that's that tangent line. And if you remember from pre-calc, the tangent is actually the distance along this tangent line from the arc, the termination of the arc, to the x-axis. So that's going to form the tangent, the tangent. We've got another triangle here formed by the cosine and the sine, and this, of course, is 1 here. And so what we're going to do is we're going to compare 3 areas, okay? So that's going to be our strategy here. So we want to show, we'll write our introduction, we want to show that sine of x over x goes to 1 as x goes to 0. And the way we're going to do this, our strategy, is we're going to compare the large so we're going to compare the small triangle, the sector, and the large triangle on the diagram, and then use 2 cups. The small triangle, the sector, and then we're going to apply 2 cups. So let's start this. The small triangle is this one right here. And we're comparing the areas. I should say here, and when we're comparing the areas. Okay, so we're going to compare the areas of the small triangle. So the area of the first one is, the area of this is 1/2 base times height. Okay, so the first area I'm going to compare is 1 over 2 sine, so I'll add a little work text here from the diagram. Right, so I've got 1/2 cosine of x times sine of x. So that's the first one. My next one is going to be the sector, the sector here, bordered right here of x. So the sector is that area there. So I have 2 triangles here. This one, and then this sector, well, not really triangle. This sector here, this is x over 2. And then I've got my larger triangle. So my larger triangle is going to be this area bound here. And if you look at this area right here, this right here was 1. And this right here is the tangent. So if I kind of lean this over, on its side, you'll see that 1 here, if I just flip it down, 1 here would be the base, tangent would be the height. So if I ordered this, right, if I stuck this down at here, here's the hypotenuse is right here, and then this is the height. So that's tan of x, and that's 1 there. So I just kind of rotated that one. And this area then is 1/2 base, which is 1, times the tangent of x. Okay, so this triangle, so I've got this is less than 1/2 the tangent of x. Okay, so this right here was the small one. This right here was the sector. And this right here is the large one. All right, so those are my 3 triangles there. Now what I'm going to do is I'm going to do the first natural thing that occurs to me, which is to get rid of the 1/2. So what I'm going to do is multiply by 2 and just get rid of the 1/2. The other thing I'm going to do here is I'm going to convert tan to sine over cosine. Okay, so now I have this inequality right here. And remember, what I want here in the middle is sine of x over x. So x is on top on this one. What I'm going to do is I'm going to flip everything. And remember, when you flip everything here, when you flip everything, you have to flip the inequalities. Okay? So what I'm going to do is 1 over cosine of x sine of x is greater than or equal to 1 over x is greater than or equal to cosine of x over sine of x. And remember, I can do that because I'm talking about x near 0. I'm not talking about x at 0. I'm talking about x near 0. It should be noted here that I'm also only messing with the right side. And I should do a diagram for the left-hand side. I'll leave that as an exercise for you. Okay, so I flipped everything in here. And remember that sine of x is not actually 0. We're talking about near 0. Okay, now what I'm going to do here is I am going to go ahead and I'm going to multiply through by sine of x. Now, sine of x, so let's put that up here. Let x right near 0 So what we're going to do is we're going to talk about, again, right near 0. So we're talking about the positive side here. Okay, so x is greater than 0, sine of x, and it's going to be, since x is right near 0, right? Because it's greater than 0, but it's less than 2 pi. I'm sorry, not 2 pi, pi over 2. So it's less than 90 degrees. I'm talking about sine from 0 to 90 or from 0 to pi over 2. Okay? Thus, sine of x is greater than 0. So when I multiply through, I preserve the inequalities. I don't flip the inequalities. And that's going to look like this. So when I multiply through by sine, I'm going to have 1 over cosine of x is greater than or equal to sine of x over x, which is greater than or equal to cosine of x. Okay? So my top is going to be this. This is going to be bot. And I've got my first condition. Okay. Now what I'm going to do is, now that I've got that, I still need my second condition. So my second condition was that everything has to go to 1. Okay. So I need to do the limits of these things. So, and remember, I'm on the right side, so I'm just going to do it like this. The limit as x goes to 0 from the right of 1 over cosine of x equals, now, because this does not equal 0, I can use the quotient law. So I have the limit as x goes to 0 from the right of 1 over the limit as x goes to 0 from the right of cosine of x. Now, from before, from our previous thing, if we slip on up here, we know that this limit right here is 1. So that gives us and that word says lemma. So that was, I'm kind of calling the thing above a lemma. I'll just change that. We'll say that previous. This is LC for the top, above for the bottom. I get 1 over 1. And this week that equals 1. Now I do the other side. The limit as x goes to 0 plus of cosine of x equals, and then I do prior. That equals 1. We proved that prior, above, whatever. Either way. And then I'm just going to say, thus the second condition is met. Therefore, by 2 cops, I know that the limit as x goes to 0 of sine of x over x equals 1. Okay? And this is going to be an important fact. So we need this fact in order to prove that the derivative of sine is cosine. And to prove that sine has the direct substitution property, which is nice, and cosine. So this is the thing that, and I should say that I only did the right side. So the right side, not the left side. So the left side is left for you to do. Again, you flip everything. Things become negative instead of positive, and you can work it out. Okay, so that is how you do this major proof. Okay, so let's talk about the structure of the introduction and how proofs are graded. So if we look up right here, notice what I did. I did this want to show. And when I said want to show, I restated the problem in my own words. Here, okay, it's just a minor restatement. But look at this first one we did. And the first one we did, way up here, the want to show was a significant step in and of itself. Because the want to show said, I took the definition of what it meant to be a polynomial and I stuck it in. And by doing that, I immediately got exactly what it was I wanted to prove and basically the way to do it. So I said I want to show, and then I said a way to do it. Here, my strategy was very short. I said apply limit laws. Here, my strategy was a little longer, and here it was longer still. So your strategy, you kind of want it to be the thing that you would have to memorize. The want to show and the strategy, basically your entire introduction, should be the thing you have to memorize in order to reproduce the proof on your own. So a couple of things that usually go in the introduction, okay? So here's what I want in my introduction. I want my, the want to show, okay? So I want to say what it is I want to do, and I want to state it in my own words, okay? The next thing you want to do is to write your strategy. So what I'm going to want to do in my strategy is I'm going to say how I'm going to do it. And be sure to state any of the name theorems you used, okay? So here I'm using 2 cops. Notice here in my strategy, I stated what I was going to do. I'm going to compare the areas of the small triangle, the sector, and the large triangle on this diagram. and then I'm going to apply 2 cops. And that's a very short way of saying what it is I'm about to do. Okay? Any intuition would go here, and any pictures, any intuition, and then any diagrams. Okay, so this is not the type of diagram I'm talking about. This is the type of diagram I'm talking about. So if I'm writing my introduction, this really isn't part of the proof, but it's kind of the intuition going on here, is that this, we're going to squeeze, or we're going to 2 cops this thing together. This 2 cops are going to be the absolute value of x and the negative absolute value of x, which is where we'll get to eventually. But the idea here is that any intuition that goes in, any intuition or pictures that aren't part of the proof should go there in part of your, as part of your strategy and your part of introduction. The other thing I'm going to put in here is any rabbits. And we're going to talk about rabbits later. We're not so much talking about them now. Is it 1 T or 2 T's in rabbits? Interesting. Okay, but this is any rabbits or other magic tricks. Okay, a rabbit is a special 1 that I multiply by, or a special 0 I add. Okay, because I'd always add 0 and I could always multiply by 1. And we'll talk about rabbits later. So those are the things that go into my introduction. Now, let's look at why this writing an introduction is important. It's important just to, there are a couple things that it's important about. So let's talk about that real fast. Okay, reason to write your introduction. Reason to do this. And it should be emphasized that I don't have to write an introduction. I could get away with not writing my introduction, but I have to have a pretty perfect proof, right? So if I just started here and went down, I would actually get the full points. But if I forgot something or missed something, I'd lose points. And the other reason was, so the first is kind of a cover your butt, okay? So easier to read proof. Cover your butt. Okay. And the other reason we want to do it is because you want to do this for yourself because you memorize your introduction, not the whole proof. So if you're trying to memorize a theorem, and we don't really have one for part 1 for module 1, but when we get into module 2, you'll see this. We'll have theorems that we expect you to memorize and reproduce on the test. And the way you memorize these is you write your own introduction, right? You write what you want to show in your strategy and any rabbits, and then you memorize your introduction. Then you reproduce the proof from the introduction. So to memorize a proof, this is what you do. Okay? The first thing you do is figure out what they want to say. And then what you want to do is you want to outline the steps. And then write an overall strategy. Okay, so what you want to do is you want to build your introduction. Then try to reproduce So what you want to do is you want to figure out what they want to say in your own words, outline the steps that they did, write an overall strategy for the proof, and then try to reproduce the proof from your own introduction. And if you do this, I'm telling you, no power in the verse can stop you. Okay? This is what you want to do. All right? So, let me show you what the rubric looks like. I already flipped to it once, but let's just flip back to it. So, as you can see here, the rubric is, and this rubric is available down there in the description. But the first thing we want to do is and this is a meta rubric. I should emphasize that this is a meta rubric. It's a rubric that we use to make rubrics for the problems. So you can see this, let's say this is a 15-point problem type thing, okay? Student demonstrates understanding of the problem either by restating the problem in her own words, drawing a picture, or writing a flawless proof. Strategy, overall strategy laid out, easy to follow, will correctly solve it. Okay, now look at this. Of 15 points, look how many were in the introduction that I could secure in my introduction before I did anything else, right? I can secure 7 of these points of a long proof right off the bat just by writing a few sentences. Then the details always say, like, stating the name of the theorem, okay? So if I have a, like 2 cops, if the rubric that will happen will have state 2 cops, state that you use 2 cops in the details section of the rubric. But look, I've picked up that point from my introduction. So even if I forgot, even if I came back, so for example, if I came back here when I did my proof, if I had forgotten to state therefore by 2 cops, if I just said therefore the limit as x goes to 0 sine of x over x equals 1 QED, I didn't state the theorem I used, but note, I stated it up here. So my butt is covered. Okay, I still get the point for stating what the name of my theorem was. Okay, now, just to look at the other piece of the proof, you've got fluency here and neatness. Make your proofs neat. It's easy. 2 drafts if you can. Fluency, just that you're using the symbols correctly. So it's a language issue, right? Okay, and if you do all of these things, you'll have excellent proofs. And I cannot stress this enough. If you write an introduction to your proof, you want to write an introduction to your proof because then the grader will see your introduction, you'll secure a whole lot of points, and then if you have a really nice introduction, the grader will skim your proof, right? The grader is moving very quickly, has a lot of these things to grade, doesn't want to spend a lot of time. If you show you know what you're doing in the introduction, the grader is going to skim your proof for like 1 or 2 other little details and then move on to the next student. All right, so you might get away with something small if you write your introduction. So really, write your introduction. That is the big #1 thing that I can say for this whole thing. Write introductions to your proofs. If you get nothing else out of today, write introductions to your proof. Write introductions to your proofs. Okay, that's what I have for you. Thank you very much.